Hello there, Mr. Sutton here, bringing you the AB Calculus 414 Extra Practice Number 3 solutions on basic related rates. On this problem, when it really comes down to it, they're giving us this formula here for Charles' law that relates the volume and temperature of a gas, and they just want us to write a relationship for the rate of change of volume and the rate of change of temperature with respect to time. So this is basically the beginning of a related rates problem where you just have to take the derivative of everything with respect to time. So derivative of volume, that's going to be dV over dt. And derivative of the right half of the equation, since c is a constant, it's going to be c times, now we have to take the derivative of t with respect to time. So that's going to be d big T over dt. And there really isn't anything else to do on this problem except pick this out of the answer choices. So that's going to be choice B. On this problem, we have a rectangle with width W and height H. And they're telling us the width is twice the height, which is going to be important in a moment. And then they're telling us the dimensions are both functions of time. So that includes W and H. And also, honestly, the area is also going to be a function of time. So if A is the area, we want to know which of these equations gives the rate of change of A with respect to T. So basic idea, looking at these answer choices, you have multiple rates of change going on. This is essentially a related rates problem. So we're going to start with an equation that ties everything together, which is just going to be area equals width times height. Now the key on this one is they told us that the height, or the width rather, is twice the height. So instead of writing W here, I could write 2h instead. And doing that is going to allow me to get one of these answer choices in a few moments. So let me write this as 2h times h, or 2h squared. And at this point, to get one of these answer choices, I have to take the derivative of a equals 2h squared with respect to time. So implicitly differentiate and basically give everything a d, whatever the letter is, over dt tail. So derivative of a is going to be dA over dt. Derivative of 2h squared, that's going to be 4h times dH over dt. And that is going to give us, let's see, which answer choice? Oh, the units are important too here. So how do we know which units we're using? Well, the key on this is looking at the thing that you isolated, the dA over dt. This is what we're ultimately getting, the quantity that we're describing, the change in area with respect to time. So the top of the fraction has area units. That's going to be, in this case, square inches. The bottom of the fraction has time units. That's going to be seconds. So this should be square inches per second. So we need 4h dH over dt square inches per second. And that's going to be answer choice D. For this problem, we have a person who is m feet tall walking away from the base of a street light along a straight road. We've got a nice little picture of this. Height of the street light is L. And basically we have both the person's distance from the street light and the length of the person's shadow changing over time as this person walks away. Now, sometimes they would ask you to actually set up an equation that related all this stuff, but in this problem they gave you the equation. 1 over L times x plus s equals 1 over m times s. So what all they want us to do is figure out the relationship between the rate of change of x, which is how far you are away from the streetlight, and the rate of change of s, which is how long your shadow is. So we essentially just need to take this equation and treat it as a related rates problem. So let's start by, just to make my life a little bit easier, I'm going to multiply both sides of this equation by L. And part of the reason I'm doing that, honestly, is because I'm looking at the answer choices and I'm seeing an L over M in all of them. So if I multiply both sides by L, I'm going to get an L over M, which would be a great step towards matching one of these answer choices. Next thing I'm going to do is I'm going to take the derivative with respect to time of everything here. So going from left to right, derivative of x, that's going to be dx over dt. For s, we're going to have ds over dt that we're adding there. And on the right side, L over M is a constant, so it's just along for the ride. So we're going to get L over M times ds over dt. And if you look at all these answer choices, they've isolated dx over dt. So to do that, I'm just going to subtract ds over dt from both sides. And that gives me one of these answer choices. It looks like that's going to be answer choice D. For this problem, we have a particle moving on a circle with this equation. And we want to know at the time when the particle is at the point 3, 4, and dx over dt equals 6, what is the value of dy over dt at this time? So since we have multiple rates of change involved in the same problem, this is a related rates problem. We're going to start by taking the equation they gave us, which we don't have to find on our own, thankfully, and differentiating everything here with respect to time. That's going to give us some dx's and dt's, and we can hopefully solve for the dt that comes out of this process. So taking my derivative for each thing, we've got derivative of x squared, which is going to be 2x, times the tail of dx over dt. So everything in here, x and y, they are both functions of time in this setup. And then for y squared, that's going to be 2y times dy over dt. And that's all going to equal the derivative of 25, which is just 0. So again, I'm solving for dy over dt at some point. So that means I have to plug things in for these other three unknowns. So for x, we've got the x value of the point that they gave us for our particle. That would be 3. So we have 2 times 3 times dx over dt, which they came out and told us was 6, plus 2 times the y value, which is the 4 from this point. And dy over dt, that's what we're solving for, so that's just going to hang around. And that all still equals 0. So let's see here. This is going to be 6 times 6, so 36, plus 8 dy over dt equals 0. So we can say 8 dy over dt then equals negative 36. And then if we divide here, negative 36 over 8, we can reduce that by 4s to negative 9 over 2, which is going to give us answer choice D. For this problem, for times 0 to 8, people are arriving at an outdoor concert at a rate modeled by this A function. And by the way, this is a calculator problem. So it would probably be a good idea to plug this A function into your calculator. And now for times 0 to 1, they're telling us no one is leaving. But for times 1 through 8, people are leaving. They didn't like what they heard, so they're starting to leave. And that rate at which they are leaving is modeled by this L of t function, which it would also be a good idea to enter in your calculator, maybe as y2. And these are both measured in hundreds of people per hour, where t is measured in hours. At least this is important when we write our units on these problems. And the number of people in the venue in hundreds at time t is given by the function p of t. So they didn't tell us what p of t was, but when we refer to the number of people at this venue, we are going to use p of t to symbolize that. Okay, so first part here. At time 2, there are 600 people in the venue. They want us to write an equation for the locally linear approximation of p at time 2. So they basically want us to write p of t is approximately equal to, and then they want some kind of tangent line setup. And then they want us to use that tangent line setup to approximate how many people there are at time 2.5. Okay, so to do this, we're going to need to know really two things. We need to know how many people are already there at time 2, which they already gave us. They said at time 2 there's 600 people. And we also need to know the derivative of p. Because our general setup for tangent line approximations, you have f of a, your launching off point, which is the t value 2 in this at this problem, f of a plus f prime of a times x minus a. So we need to figure out what f prime is going to look like, in this case p prime. So the rate at which the number of people is changing, that's going to be equal to the rate at which people are arriving, a of t, minus the rate at which people are leaving, L of t. So p prime we can define, and this is only, by the way, for times 1 through 8, because nobody's leaving from time 0 to 1. But from times 1 to 8, which is when this time falls in, we can define p prime as a of t minus L of t. And at this point, I'm just going to go and put all of this on my calculator. So here I am in my y equals. In y1, I've entered the a of t function carefully, and then in y2 I've entered the L of t function. At this point, I'm going to enter a function for p prime, because I have a feeling I'm going to end up using this multiple times on the problem. So we said this was just a of t minus L of t, which means here I can just do alpha trace, pull up my y menu, and put y1, which is the a function, minus alpha trace. Let me select y2, because that's the L function. So there's our p prime in y3. Okay, let's keep going here. So we can say that p of t then is going to be approximately equal to the number of people at time 2, which we said was 6. I'll write 6 to represent the 600 here. Plus, we're going to have p prime of t, in this case p prime of 2, because our launching off point is 2, times, and now we're going to have t minus 2, because again 2 is our launching off point. So this is essentially f of a plus f prime of a times x minus a. All we have to do at this point is enter this in the calculator and then plug in 2.5. So let me go and do that now. So back in my calculator, I'm going to enter this now in y4. I've got 6 to represent the 600. So there we go, 6. Plus, now I have to do p prime of 2. Well, p prime is y3 in this setup, so I'm just going to do alpha trace, and then I'll select y3, and I'll just plug 2 into that. And next to all that, I'm going to have x minus 2. This is where the variable is actually going to do its work. So x minus 2. There we go. And now let me just quit out of all of this, and I actually need to plug in 2.5. So I'm going to do alpha trace, and now let me select y4, and I'll plug 2.5 into all that craziness. So there's many levels of functions going on here, and hope for the best. So this comes out to about 6.201. We'll just round it off to 3 decimals. And that's going to be, let's see here, they wanted to know the number of people. This is going to be in units of hundreds of people. So I guess this is really, if you're doing a real-life approximation, this would be 620 people. That tenth of a person doesn't really count. But they didn't say to round it off to a specific number, so we're allowed to give it in this format. For this part of the problem, they want us to find p double prime of 5, and then using units, interpret what that actually means in the problem. So we've already gotten p prime defined. Remember from part A that was a of t minus L of t. So to do p double prime of 5, we're actually allowed to just take the derivative of this function with 5 plugged in directly on the calculator without actually showing what p double prime looks like algebraically. So let me go and do that on the calculator. So just to review what I did in part A, here's where I entered everything. y1 was a of t, y2 was L of t, and y3, this is the most important part, this was my p prime of t right here. So let me quit out of here now, and I'm going to do math 8 to get my derivative. I'm going to do dx, and I'm taking the derivative of y3 because that's where I stored p prime. So if I do derivative of y3, that's going to give me p double prime, which I want to evaluate. They said at 5, so let me go and plug in 5 here, and that's going to equal negative 0.679. Okay, that's great. So what are the units going to be? Well, the units on p prime, this was the rate at which people were changing. This was in hundreds of people per hour. So the rate, if I take the derivative of that with respect to time, I'm going to get people per hour squared, or I guess hundreds of people per hour squared. Like so. Now, we haven't actually answered the whole question. They want us to interpret the meaning of p double prime of 5. So what this means is that at 5 hours, we have to always put the time unit in there. At 5 hours, the rate at which people are changing, which is p prime, that rate itself is changing at a rate of negative 0.679 100 people per hour squared. On this part of the problem, they're asking if there is a time between 1 and 8 at which the rate of change of the number of people in the venue changes from negative to positive. Give a reason. Okay, well, probably the easiest way to do this, since we've already got that rate defined as p prime, is to just figure out graphically where p prime, which equals all this stuff, changes from negative to positive. Let's just do that on our graphing calculator now. So to do this on the grapher, I'm going to go back to my y equals, and I've got a whole bunch of things entered in here. Remember, p prime is this y3 right here. So I essentially want to graph y3 and figure out the x-intercept where it's changing from negative to positive. To do that, let me deselect everything else. I don't want to graph all these other things. I just want to graph y3 where I've stored my p prime. And I don't want to graph it on any old window. I want to use the window that they said here from 1 to 8. So let me go to Window, and let me go from xmin 1 to xmax 8. And let me do zoom 0, zoom fit, and see what this looks like. And this might take a while because we're involving multiple functions that have sines and cosines, but we're just going to have to wait it out and see what this graph looks like. So it's chugging along here ever so slowly, but it looks like we have one spot where we're changing negative to positive, right about here. So let's go ahead and find what this spot is. Let me do second, trace, and zeros, and let me move my spider in this direction. It's like a roller coaster. Whee! And then press enter a little bit to the left of my intercept, and enter again a little bit to the right, and enter one more time for kicks and giggles. And this comes out to about 6.5479, so 548 if we round that off. So there was my graph. And this happens at time 6.548 hours. So the answer to the question then, is there a time where this changes from negative to positive? Well, the answer is yes, and here it is. For the final boss battle on this particular problem, we have a rectangular standing only section, which changes in size in order to manage the flow of people. And this is all happening with respect to time. X is the length of this thing. Y is the width. This is all measured in feet. And they're telling us the length is increasing at a certain rate, the width is decreasing at a certain rate. We want to know the rate at which we want to know the rate of change of the area with respect to time when the x is 16 and the y is 10. So we have multiple rates of change going on here. This is a related rates problem. We're essentially trying to find the derivative of area at a certain time. So to do that, we need to set up a general equation for the area and then differentiate everything with respect to time. So let me start with my overall formula that ties everything together. Since this is a rectangle and we're talking about its area, we just have area equals x times y, which is basically length times width. And now I need to take the derivative of this. So I'm going to have dA over dt, and that's going to equal the derivative of the product of x and y. So I'm going to set up my box and ribbon here to negotiate that. So I have an x, I've got a y, and I have the derivatives of these with respect to time. So dx over dt and dy over dt. So now differentiating everything, I can say that dA over t equals, and now using my ribbon here, we've got y dx over dt, and going the other way, plus x dy over dt. And ultimately, I'm solving for dA over dt. This is the change in area with respect to time. So I just need to plug in the values of these four things at the time that they're talking about in the problem. And they gave us all these numbers. So the y here they gave us, that was 10. They gave us dx over dt. That was the change in, let's see, x is the length. So they said the length is increasing at a rate of 6. So this is going to be a positive 6. And then x, they told us right out here was 16 rather. And then for dy over dt, well, y is the width. They said that the width of the section is decreasing at a rate of 3. So for dy over dt, we have to actually plug in -3. So careful on that. And you could actually just stick units on this and call it a day, or you can get the final number. So we have 60. This would be minus 48, so that's 12 overall. Now, what are the units? They said indicate units of measure. Well, dA over dt, area, this is going to be measured in square feet. Time is measured in hours in this problem. So this is going to be square feet per hour, so 12 square feet per hour.